Welcome back to the fourth and final installment of section 6.1. And in this final installment, we're going to learn how to conduct hypothesis tests using the new formula for the standard error that we've developed here in section 6.1. What this is finally going to allow us to do is conduct a hypothesis test without having to rely on simulation at all. By the time we're finished with this material, we will no longer have to refer to a randomization dot plot to conduct our hypothesis test. Now, at the end of this little part 4 here, we're going to work a couple of problems. And what I'm going to do in each of those problems is walk through the 3 different ways that we can conduct the hypothesis test. And what we're going to see is we're going to start with our first method, which is complete reliance on the randomization dot plot. Then we're going to do the method that we learned in Chapter 5, which still relies on the dot plot to a certain extent, but leverages some theory from normal distributions. And then finally, we'll see how to do that same problem using theory alone. In fact, our new formula for the standard error. Okay, so we will do this when we work those problems at the end of this section. We'll work those problems out doing all 3 different methods so you can kind of see them side by side and compare and contrast them. I think that's going to be an important thing for you to be able to do. So we'll do that together. All right, let's remember where we were at the end of Chapter 5, right? Recall from our work in Chapter 5 that the randomization distribution of the sample is often bell-shaped and can be associated with a normal distribution curve. So this is just the idea that those randomization dot plots form these normal distribution shapes, and we can read the 2 parameters that form the associated normal distribution curve right out of the dot plot. We can look at the mean of the dot plot, which comes from the null parameter, and we can look at the standard error of the dot plot, which we can read out of the dot plot, and that will form the sigma of this normal distribution. Now, what did we actually do by the time we were done in Chapter 5? We said, we've got our evidence, which we can think of as our best estimate. We've got our evidence. We take that evidence and we standardize it. All right? And what does that mean? It means we subtract the mean and divide by the standard deviation. We can standardize it and make our evidence now sit on a normal scale, a standard normal scale. And then we can compute the p-value of that evidence as the p-value of that standardized score. All right, we can do that with a standard normal curve. Okay, I'll remind you of that when we go to work on the problem. But basically, we were standardizing our best estimate or standardizing our evidence and then computing the p-value relative to a standard normal scale. Now, we still relied on getting the value of SE by pulling it out of the randomization dot plot. What we're going to see by the time we finish section 6.1 is that that is no longer necessary. All right, because we'll have a way of calculating SE directly. All right, let's see what this looks like in the special context of a hypothesis test for a single proportion. All right, here's the setup. Let P be the proportion of a population that has attribute A. Suppose we want to test the claim P is different from P star. Now let me stop here and say that think of P star as some fixed number like 0.5. All right? So suppose we want to test the claim that P is different from 0.5. Okay? We can submit this to a hypothesis test. So our null hypothesis will be no, P is equal to P star, or in this specific case, P equals 0.5, versus the alternative hypothesis would be P is different from or is not equal to 0.5, or whatever the value of P star is. Now, I highlighted this just to emphasize that in place of is different from, I could say P is greater than P star, and that would be reflected in a greater than sign here, or P is less than P star, and that could be reflected in a less than sign here. So we can look at any of these 3 ways of forming the alternative hypothesis, and we would know what to do here. Okay, this is not the new stuff. All right, for a random sample of size n from the population, let P hat be the proportion of the sample that has attribute A. So we can think of that as our evidence. All right? What do we do with that evidence? We take the p hat, we standardize it, we subtract the mean, which is going to be the null parameter p star, and we divide by the standard error of the dot plot. Now, what we have available to us now is we can replace the standard error by a formula, all right? So that by the time we're done, this value of z can now be completely computed without having to make a randomization dot plot. So by the time we get to section 6.1 here, this formula here on the right can be completed fully without having to make any reference to the randomization dot plot. Now, I want you to make one special note here. Notice that the value of SE here is using P star, not P hat. It's using P star. Why? Because we're living in the world in which the hypothesis, the null hypothesis, is true. So we're really saying within the population, the true proportion of the attribute is P star. And so this is reflected here in this standard error. Okay, so this is one common mistake in computing the z-score here, is to use p hat in place of p star. You should really use p star here. Okay, but the point is that this is going to follow a standard normal distribution, and therefore we can compute the p-value of the observed statistic by computing the p-value of z, this standardized observation. Okay. Let's take a look at a couple of problems. Hopefully by the time we're done with these two problems, we'll have a complete understanding of how to do this kind of hypothesis test from 3 different stages, or 3 different methods. All right, let's take a look at this first problem. There were 2,428 Major League Baseball games played in 2014, and the home team won 1,288 of them. Okay, so we've got a total sample size of 2,428, and we've got the home team winning 1,288 of those games. The problem goes on to say, if we consider the games played in 2014 as a sample of all the Major League Baseball games, test to see if there is evidence at the 1% level that the home team wins more than half the games. Show all the details of this test. Now, we'll have to talk through the details of the test because I don't have any way to write this down until we go to the whiteboard. I'm going to do part 1 here using StatKey, and parts 2 and 3 using the whiteboard. But let's just talk through what we would do here. So we would use as our null hypothesis that P, the proportion of the games won by the home team, P is equal to 0.5. And the alternative hypothesis would be P is strictly bigger than 0.5. We're testing that claim. Now, the way we would do this, just using randomization dot plots and StatKey, and this is the chapter 4 method, we would go into StatKey, we'd say we're testing for a single proportion. We would go in here and edit the data, and we'd put in the evidence that we've actually found. We saw that there were 1,288 games won by the home team out of 2,428 games played within that season. That's our sample size. Okay? Now, when we look at this, let's just look at this before we get too crazy. It looks like the home team has won 53% of the time. Now, that is certainly evidence for the alternative hypothesis, which says that proportion is bigger than 0.5. The null hypothesis, which we have set here, or has been set already for us, we're not going to change it, because this is our null hypothesis that the home team should win half the time. All right, so is this strong evidence for the alternative hypothesis? Is this strong enough to reject the claim that P is equal to 0.5 and accept the alternative claim that P is bigger than 0.5? All right, let's go ahead and simulate under the null hypothesis how these games would come out if P were equal to 0.5. Okay, so let's generate several thousand samples. And then what we need to do is we need to find the p-value of 0.53. We're gonna think of that as a right tail calculation. We're gonna put in the 0.53, and we're gonna ask how many dots are at or to the left of 0.53. And in this case, you can see that the answer is very small, right? The proportion is 0.0014. That gives us a p-value by this method. And we're going to want to compare p-values for all these methods. This gives us a p-value of 0.14%. I'm going to write that down so we can reference that later. And we want to make our conclusion. Now, what is our conclusion going to be? Well, we were asked to conduct this test at the 1% significance level. And what we found is the p-value is well below that 1% significance level. So at this point, we would reject the null hypothesis and say that there is sufficient evidence to support the claim that the home team wins more than half the games. All right. Now, what we want to do is we want to go ahead and work the same problem through the techniques of section 5.1, so we can compare and contrast these two methods, and then finally work this problem through using just the techniques of section 6.1. And what you'll see is that we went from total reliance here in part 1, total reliance on simulation. We were doing this problem entirely using the randomization dot plot, counting dots. Here we have some reliance still on the randomization dot plot. And here we will have total freedom, total emancipation from using the dot plot and using the theory instead. Now, one thing we're going to want to grab from the dot plot as we move into part 2 is we want to get the standard error, because we have to carry that SE value along with us as we move forward. So we're going to go up here and record that the SE value on the randomization dot plot is 0.010. We're going to bring that with us to the whiteboard. And we've got a p-hat value of 0.53. We'll bring that with us to the whiteboard as well. And a sample of size 2,428. So we'll record all of that. We'll bring that with us to the whiteboard, and we'll show how to do parts 2 and 3. All right, so I'll meet you guys at the whiteboard for that. All right, welcome back to the whiteboard. Now we're going to work part 2 of problem 6.56. And this is where we use our mixed strategy of section 5.1. So let's just remember the context for this problem. We've got the 1,288 games won by the home team. We're dividing that by the total number of games played that season, and that gives us a proportion of games won by the home team in this sample of 0.530. The SE that we pulled from the dot plot was 0.010. Now, the claim that's being made is that the proportion of Major League games won by the home team is greater than 0.5. So if we put this into the context of a hypothesis test, the null hypothesis and the alternative hypothesis would be that the proportion of games won by the home team is 0.5 against the alternative that it's greater than 0.5. And so we're just trying to see if the sample provides enough evidence for this alternative hypothesis. Now, how do we do that in our mixed strategy? We standardize this 0.53 and we put it onto a standard normal scale. So we take the 0.53, we subtract the 0.5, the null parameter given to us by the null hypothesis, and we divide by the standard error that we got from the dot plot. When we carry out this calculation, when we do the 0.53 minus the 0.5, that gives us 0.03. When we divide that by 0.010, we get a z of 3. Okay, to finish off this problem, all we have to do is take our standard normal curve and find 3 and calculate the area that sits, because this is a right-tailed test, we're going to calculate the area that sits to the right of 3. And when we have StatKey do that calculation, we end up with 0.0013 or 0.13%. Okay? Now, we're being asked to do this hypothesis test at the 1% significance level, and 0.13% is certainly less than 1%, and so we would reject the null hypothesis and we would accept the alternative hypothesis as a better explanation of this evidence, And we would certainly say that there is sufficient evidence to support the claim that the proportion of Major League Baseball games won by the home team is greater than 0.5. We found enough evidence in the sample to make that conclusion. Now, we're simply going to finish up problem 6.56 by using the techniques of this section alone to do this calculation. Now, much of this stays the same. All we're going to do is, instead of using the standard error that's provided by the dot plot, we're now going to calculate the standard error from theory alone. And what does our theory tell us? It says that the standard error should be calculated by using the p that comes from the null hypothesis, 0.5, times its complement, which in this case is also 0.5, divided by the total sample size, which is 2,428, and that's going to give us the new standard error. I'm going to take the square root of that and calculate it. I get 0.010, which is identical to the standard error that we got from the dot plot. So the rest of this calculation would look exactly the same. We would take our standard error just as before, and we would say, all right, how do I standardize my observation? I take the 0.530, I subtract the null parameter, I divide by the standard error that we've now calculated through theory, and that's going to give me the z-score, which is 3. We would weigh that evidence. We'd calculate the p-value just as before. We would end up with exactly the same p-value as before, and we would draw exactly the same conclusion. We would say that there is sufficient evidence to support the claim that the proportion of Major League Baseball games won by the home team is greater than 0.5. So what we see here as we move from strategy 1 to strategy 2 to strategy 3 is, in strategy 1, we use the randomization dot plot to do all of the work, including counting all the dots in the right tail. In strategy 2, we grabbed the SE from the dot plot, so we had a mixed strategy, some theory, and some simulation coming from the dot plot. In particular, we used the dot plot to help us get the value of this standard error. In part 3, we used the techniques only of this section, and so we were able to calculate the standard error through theory alone, and we found perfect agreement in this case between the theoretical standard error and the standard error that we got from the dot plot. So the rest of the problem is identical. All right, so that draws a conclusion to problem 6.56. Let's go look at one more problem in conducting hypothesis test. All right, so we have one last problem we're going to want to look at here in part 4 of section 6.1. This is another hypothesis test. I thought it would be good to do one more of these just to give you a chance to see all of these methods. And if you want to try to go ahead and work this problem, read this problem along with me, and then try to work it out on your own ahead of time, that would be great. And then we can you can test yourself, and we can see if we're getting the same answer. So go ahead and try to do that if you want. Stop the video at some point and try to work these out all on your own. All right, let's read the question together though. Multiple choice questions on advanced placement exams have 5 options: A, B, C, D, and E. A random sample of the correct choice on 400 multiple choice questions on a variety of AP exams shows that B was the most common correct choice, with 90 of the 400 questions having B as the answer. All right. Does this provide evidence that B is more likely to be the correct choice than would be expected if all 5 options were equally likely? Show all the details of the test. Use a 5% significance level. All right, so what's this question getting at? So if those 5 choices, A, B, C, D, and E, were to occur with equal frequency, we'd expect B to show up as the correct answer with proportion 0.2. So that's going to be our null hypothesis. All right, P equals 0.2. The question is there evidence to support the claim that P is actually, and P again is the proportion of times that B is the correct answer. Is there evidence that P is strictly bigger than 0.2? All right, so we've got a one-sided right-tailed kind of hypothesis test here. So the first thing we're going to want to do, we're going to do this through all three methods. Chapter 4, Chapter 5, and Chapter 6 each have their own method. We're going to do this using StatKey and using a randomization dot plot, and we're going to just do this purely by counting dots and weighing the evidence just by counting dots, and then we'll show how to slowly emancipate ourselves from the randomization dot plot. So let's take a run at this through this method. So we're already here. We have to edit our data because now, in light of this new problem, we've got out of 400 questions on the SAT, 90 of them had B as the correct choice. The null hypothesis is that B should show up with proportion 0.2. And so we want to ask ourselves, is the fact that B showed up as the correct answer with proportion 0.225, is that strong enough evidence to reject the null hypothesis and latch onto the alternative that P is actually strictly bigger than 0.2? Now, how do we settle that? By the methods of Chapter 4, we simply generate lots and lots of samples under the null hypothesis, and then we take our evidence, our 0.225, and we find it in the right tail. And we ask ourselves, how unlikely would it be, right, to see a proportion as big or bigger than 0.225? And what this is telling us is that the p-value that we're seeing is 0.115 or 11.5%. Okay, I'm going to write that down. At the 5% significance level, that would be considered not significant, right? And so we would say there is not sufficient evidence to support the claim that P is bigger than 0.2. All right, so that would be the conclusion that we would draw out of this. Now, what I want to do is just grab a few pieces of information before I leave this. So our P hat is 0.225. We're going to take this to the whiteboard. And our SE, which we can get here, we can read this off the randomization dot plot, is 0.020. Now, we'll bring these numbers with us to the whiteboard. We'll work this through like we did in Chapter 5. We'll conduct the hypothesis test in a kind of a Chapter 5 manner, and then we'll conduct this same hypothesis test in a manner that's appropriate for Section 6.1. Okay, so I'll meet you at the whiteboard to finish this up. All right, so welcome back to the whiteboard. We're going to finish up parts 2 and 3 of problem 6.58. And let's just remember the context for this problem is that on the AP exams, it was found when a sample of size 400 was considered that 90 out of those 400 had B listed as the correct answer. So that's a proportion of 0.225. We saw that the SE from the dot plot, the randomization dot plot associated with this sample statistic, is 0.020. Now, the claim that is being tested here is that the proportion of times that B is the correct answer on AP exams is greater than 0.2, and there certainly is evidence in the sample for that claim. Now, the question is, as is typical, is this evidence strong enough to sustain this claim? Now, if we set this up as a proper hypothesis test, we'll see that the null hypothesis is that this underlying proportion, the proportion of times that B is the correct answer, is in fact 0.2, and the alternative is that it's bigger than 0.2, that proportion exceeds 0.2. So this evidence is certainly pointing in the correct direction to sustain this alternative hypothesis. We just need to see if the evidence is strong enough. Now, what do? In our part 2 strategy, we're using a mixed strategy. We're going to take the 0.225 and we're going to standardize it. So to get its z-score, we're going to take the 0.225. We're going to subtract the null parameter, the 0.2, and we're going to divide by the SE, which in this case is provided to us from the dot plot. So that's 0.020. All right. When we calculate that, we're going to get 0.225 minus 0.2 divided by 0.020, and we get 1.25. Now to weigh this, to calculate the p-value of this evidence, we just have to put this on a standard normal scale. And calculate how much area sits out in this right tail. Okay, when we do that calculation using stat key, we find that this is 10.6% of the area. So the p-value is 10.6%. And if we're working at a 5% significance level, this is not enough evidence. This is not below the 5% significance threshold. So in this context, given this p-value, we would not reject the null hypothesis. So we would not find this evidence enough to reject the null hypothesis. So in this case, we would simply say there is not enough, or there is not sufficient evidence to support the claim that the proportion of times that B is the correct answer on AP exams is greater than 0.2. Now, is there some evidence in the sample to support that claim? Yes, there is. Is there enough evidence, or is there sufficient evidence to support that claim? There is not at the 5% significance level. So that is how we would work this problem using a mixed strategy like from section 5.1. Now what we want to do is do this one last way, and this is using theory alone. So now we have to imagine that we don't have any simulation to help us find the standard error. We're going to find the standard error using our theory. And if we use the theory alone to find the standard error, what we get well, according to the theory, we're working under the null hypothesis, so we should use 0.2 times its complement, which will be 0.8, divided by our sample size, which is 400. And when we do that, we'll get 0.020. Now, that's exactly the same standard error that we got from simulation. So the rest of this calculation is going to look exactly the same. So if we were doing this by theory alone, we would get our standard error from our theoretical calculation. We would take our evidence, the 0.225. We would subtract the null parameter. We would divide by the standard error. And we would produce the z-score, the same z-score that we produced earlier, right? Nothing else has changed. This is still 1.25. Again, we would put this on a normal scale, calculate the p-value just as we did, and proceed. And we would come to exactly the same conclusion. We would still find that the p-value of this evidence is 10.6%, and we would still say that there is not sufficient evidence to support the claim that the proportion of times that B is the correct answer on AP exams is greater than 0.2. We'd come to exactly the same conclusion because our standard error from simulation agrees exactly with our standard error from theoretical calculation. So that brings a conclusion to problem 6.58, and that draws a conclusion to this video lecture. So we'll join you on the next one.